In this video, we're going to look at sampling distributions of sample means. And we're going to answer the questions, what are they, and why do we use them? Let's start by looking at a population of size n. Here we have a population distribution for this population. And we are measuring for each individual, everybody in the population, we're measuring a characteristic, for example, height. And so each bar in this distribution represents an interval of the heights, where the smallest height is horizontally on the horizontal axis here, and we work our way out all the way to the right, and this would be the tallest height. So we have them in intervals or bins. And we have a count of how many people from the population fall in each interval. And that would give us the height, gives us the vertical axis here. So the vertical axis tells us the count or frequency of people or individuals who have a specific or fall into a specific height interval. Notice that this distribution is not smooth. It becomes smooth when we make our intervals smaller. As our bars become not as wide, more thin, this will smooth out. And if we look at this distribution, it does not look normal. As a matter of fact, it looks skewed to the right. Right-skewed population distributions often occur with things like income or home prices, where most people have lower to moderate incomes or home prices, and fewer individuals have much higher incomes or higher or more expensive home prices. When looking for the probability of a certain data value or set of data values occurring within a population distribution, the empirical rules and z-scores only work when the population is normally distributed. But in the real world, many populations, like income and housing prices, are not normally distributed. So the question is, how can we describe probabilities when the population isn't normally distributed? We start by taking multiple samples from the population where each sample is size n, and n, we want it to be greater than or equal to 30. It must be large enough. Now our population has a mean or average, which we call mu, and a standard deviation, which we call sigma. And each one of our samples also has a mean, which we call x bar, and a standard deviation, which we call s. However, since there are multiple samples, we have to subscript these. So I'll give each one of these has an x bar with an s, and I'm going to have to subscript each one of these. So this would be x bar 1, s sub 1, x bar 2, s sub 2, and x bar 3, s sub 3, and so forth. So each individual sample of size n will have a different mean or average and standard deviation. Next, we're going to take the mean from each sample and we're going to put them together. Let me grab this mean. Into another distribution, and this distribution is made up of the mean or average score that we got for each sample. So here we have each mean is taken from the sample and fed into another sample. And this new sample is the sampling distribution of sample means. And when we pull all of these means into this sample, we get a normally distributed distribution, which is what you see here. So I'm going to pull these into the distribution. We don't know really where they would fall, but these means are making up this distribution that we see. And of course, there are quite a few more, but this just happens to be just sort of a visual, so you get an understanding of it. So then we have a new mean, and the mean for the sampling distribution of sample means is mu with an x bar subscript. And the standard deviation, also known as the standard error of the sampling distribution of sample means, is sigma with a subscript of x bar. So this distribution is related to the original population distribution as follows. The mean for this sampling distribution of sample means will actually be equal to the mean of the population. And the standard deviation for the sampling distribution of sample means that we created is equal to the standard deviation of the population over the square root of n, which is the size of the original samples. So these are the samples that are of size n. Which must be greater than or equal to 30. And our standard deviation here for the sampling distribution of sample means is also known as the standard error. And this is the central limit theorem, that this distribution, the sampling distribution of sample means, will be normally distributed, and that the mean of the sampling distribution of sample means equals the mean from the population, and the standard deviation or standard error of the sampling distribution of sample means is equal to the standard deviation from the population divided by the square root of the sample size of the original samples that were taken with replacement from the population. So here is a population distribution, which is population ages, that I generated with AI, and it was based on Greenville Technical College's population. The actual population is closer to 10,000, but in my sample, I used 20,000 data values. And the model is based on IPED's proportions, but it contains no real student records. It's realistic in that the ages are right skewed. So it is consistent with the Greenville Technical College demographic profile. So here my population age, or capital N, which is the size of the population, is 20,000. And you can see that this population is right skewed, and its mean, let's write this down, which I have written below. The mean of this population is, I should put it proportionally, is approximately 24.48 years. That's the average age. And the standard deviation, sigma, is approximately 6.98 years. So that's our standard deviation, and there's our mean or average age in years. So let's look at different sampling distributions of sample means from this population using different sample sizes. So here we have a sampling distribution of sample means, where we took 200 samples, and each sample of size 5. So we took 5 data points from the original population and we took them randomly and we found their mean. And that was our first mean. And then we found our second mean and we put these 5 data points back because we do this with replacement. So we want always to be pulling one of our samples from the same population. So we put back with replacement. And so we do this 200 times and we end up with 200 means or averages of the 5 data points that we took. And those 200 data points represent our sampling distribution of sample means. And here is the distribution as a histogram. The population mean and the sample distribution mean are both approximately the same. There are 2 kinds of standard deviation. One is the theoretical standard error, which we calculate, which is equivalent to the standard deviation of the population divided by, in this case, the square root of 5. And it's 3.12, which is pretty close to the observed standard deviation that we would have calculated from all of these data points. And these data points are each represent a mean of one of the samples. So these are new data points. And so we see that the standard deviation that's actually observed or calculated is pretty close to the standard deviation that we would theoretically calculate. And our distribution is looking a little more normal, but not quite normal. And that's because n is 5. And remember, we want n to be 30 or greater. So let's look at n equals 30. So here's our next sampling distribution of sample means. And this time n is 30. And we repeat 200 times. So we have 200 samples. Each sample contains 30 randomly selected data points from the original population. We find the mean or average for each individual sample, and we put that into our sampling distribution of sample means. So what we see now is sequence more normally shaped, more bell curved, and this represents all of the means that were pulled from these 200 samples. Our population mean and our sampling distribution mean are approximately equivalent. Our theoretical standard error or standard deviation for the sampling distribution of sample means, which is the population standard deviation divided by the square root of 30 this time, is 1.27, which is much closer than the prior example to the actual observed standard deviation from this data set. So we see that we're getting closer, that this equation is getting closer to the actual standard deviation that came out of this, and our distribution is more normally shaped. Our next sampling distribution of sample means uses sample size 60. So we've doubled it from 30 to 60. Again, we have 200 samples. And notice that this is also more normally shaped. And our population mean and sampling distribution mean are the same. And our theoretical standard error is very close to our observed standard deviation. Here's our example. Greenville Technical College administrators want to estimate the average age of all 10,000 plus students, but they can only survey 30 randomly selected students. They record the 30 ages and compute a sample mean of 24.5. From the previous years, they know that the population's standard deviation is about 7 years, and they want a confidence interval of 95%, which is 1.96 standard deviation above and below the mean. So let's start by computing the standard error, which is sigma sub x bar, because it's a standard deviation. It's a theoretical standard deviation of the sampling distribution of sample means, and it's equal to the standard deviation of the population divided by the square root of n. So we're given that the standard deviation of the population is about 7 years, and n is 30, so it's a square root of 30. And this calculates out to be approximately 1.28. So for a 95% confidence interval, what we want to do is imagine here's my normally distributed sampling distribution of sample means. And we're saying, so here's our center. And I'm going to put this is a 0 for our z-score. And we're saying that the z-score should be above and below, which is 1.96 standard deviations above and below. So here's one standard deviation above. So we can go 2 standard deviation, 3 standard deviation above. And then we can have, say, 1, 2, 3 standard deviation below. So -1, -2, -3. Since it's impractical to obtain all possible samples, the central limit theorem ensures that one random sample's means is a reliable representation of the center of the sampling distribution. So we're going to consider the center of our sampling distribution to be that 224.5, right, which is the mean from that one sample of 30 that was taken. Now, what we want to do is we are trying to find the 95% confidence interval, which means that we're going to look for a z-score here, which is the 1.96. That's coming from right here, standard deviation above a z-score of 0, and then 1.96 below. So this is a z-score of 0, so -1.96. And that means that this area between -1.96 and +1.96, that gives us our 95% confidence interval. So here, 95% is everything that's highlighted in yellow. So that's 95% of our data within this distribution. So now we want to find the ages. So what would the actual ages be? Say age number 1, the lowest age, to the highest age, so age number 2, that are within this confidence interval. So this is age number 2. What are these ages? So the lowest age, we're going to take the mean, the center age, and we're going to subtract that 1.96 and multiplied by the standard deviation of the sampling distribution. And of course, the mean is 24.5 minus 1.96 times the standard deviation of the sampling distribution, which is, we calculated, is 1.28. And this gives us approximate age of 22 years. So there's our first age. And then we're going to calculate the second age. And this time, we're going to add, instead of subtract, we're going to add 1.96, get rid of that, times the standard deviation to the mean. And so the mean is 24.5, and we're going to add 1.96 times the 1.28, which is the standard deviation of the sampling distribution. And this is approximately equal to 27 years. So the estimate, when they estimate the average age of all students, we can say that the average age of all students are between 22 and 27 years old.